this third part on the basics of sets, we're going to look at some other fundamental set concepts. The first thing we're going to look at is what is the cardinal number. The cardinal number of a set is the number of elements in the set. So it's the number of elements in the set. So if I were to have set A, the cardinal number is represented by the symbol N of A. So this is how we write and represent the cardinal number of a set. So here we have 4 examples of sets. We're going to find the cardinal number of each set. So for the first one, our set is S equals the set of 2, 4, 6. So the cardinal number of this set S is equal to how many elements are there? 1, 2, 3. Okay. For the second set, we have S is equal to the set containing -2, -1, 0, 1, 2. So the cardinal number of this set S is equal to 5. That looks like an S. Let me write it again. Okay. Then we have T is equal to the empty set. The empty set has no elements. So the cardinal number for T is equal to 0. And then this last one, we have the set here. S is equal to the set containing 0. 0 is an element, so the cardinal number for this set S is equal to 1. It contains an element. That element is 0. Okay, next thing we want to look at is what's the difference between a finite set and an infinite set. For a finite set, this all comes down to cardinality. If the cardinal number is a natural number or 0, so if the cardinality of a set A is in the natural numbers, or the cardinality of a set A is, equals to 0, then it is finite. Finite means that there's a set number of elements in there that you can count. Okay? Infinite is if the cardinal number is not a natural number or 0. So it's just the opposite. So the cardinal number is not in the natural numbers or 0. The natural numbers is an infinite set. It keeps going forever and ever and ever and ever. You cannot give a definitive number value of how many elements are in that set. Okay? The set of the real numbers is also an infinite set. Okay? I could keep going and going and going and never be able to finish counting how many real numbers there are. Now, there are sets that are clearly finite. Letters in the alphabet, that is 26. That is a finite set. Letters in my first name, well, there's 2 ways to think about that. My first name is A, N, N, A. With repeats, I have a cardinality of 4. If I didn't include repeats, my cardinality would be 2. But both of those are finite sets. Okay? The sets are the set of numbers, natural numbers that are less than 10. That is a finite set. So let's take a look at a couple of sets and determine, is it finite or is it infinite? So A is equal to the set containing 1, 2, and 3. It has 3 elements, which is a natural number. So since the cardinality of A is equal to 3, this is finite. Okay. B is equal to a set containing 1, 2, 3, and so on. The ellipses at the end implies that this is infinite. And then C is equal to the empty set. The empty set has 0 elements. So therefore, this is finite. Okay. So finite versus infinite, hopefully, is a quick thing to be able to determine. Next, we are going to look at what it means for something to have one-to-one correspondence. Set A and set B can be placed in one-to-one correspondence if every element of set A can be matched with exactly one element of set B. Okay, so essentially, if we have two sets that have the same cardinality, the same number of elements, then they can be put into one-to-one correspondence. So looking at these sets that we have, these examples of A sets and B sets, if we were to determine which ones could have one-to-one correspondence, anything that has the same cardinality could be put into one-to-one correspondence. So this first one has 5 elements, S, T, U, V, W. And this one also has S, T, U, V, W. These both have cardinality of 5. And so therefore they can be in one-to-one correspondence. But so can these. So all of these could have one-to-one correspondence. Okay. Now, this set A, that's just S, T, U, V. It could be in one-to-one correspondence with set B that's equal to the set that contains 1, 2, 3, 4. Okay, there are different ways you could align each one. I could say S goes to 1, T goes to 2, 3 goes to U, and V goes to 4. Like, that's how they could correspond. Or I can mix it up. It doesn't matter how, but as long as they have the same cardinality, they have one-to-one correspondence. Two sets are said to be equivalent if their cardinality is equal. So we say that set A is equivalent to set B if and only if the cardinality of A equals the cardinality of B. Looking back at the one-to-one correspondence, essentially any set that has one-to-one correspondence with one another, if I have two sets that have one-to-one correspondence, then those two sets must be equivalent to one another because they must have the same cardinality. Equal sets must have the same elements, and they have to be exactly the same elements. So you can see that written out. Set A is equal to set B, and we would just say A equals B. If and only if both sets contain exactly the same elements. So if I have this set, A equals 1, 2, 3, and B equals 1, 2, 3, we could say that A equals B. Okay? Now if I said A equals 1, 2, 3, and B equals like 4, 5, 6, we could not say that those are equal. We could say that they are equivalent because they have the same cardinality, but I could not say that those sets were equal. So let's take a look at a couple of examples and determine if these sets are equivalent or equal, or both. Maybe it's possible to be both. We'll find out, right? So in this first one, in order for two sets to be equivalent, they have to have the same number of elements. Their cardinality must be the same. So A is equal to set A, B, C, D. B is equal to set 1, 2, 3, 4. They both have 4 elements. So the cardinality of A is equal to the cardinality of B. So yes, they are equivalent. But are they equal? In order for them to be equal, they must have exactly the same elements. So no, these are not equal. They are equivalent, but not equal. This example here, we have the set A equals XYZ and B equals WXYZ. The cardinality of A is 3. The cardinality of B is 4. So no, those are not equivalent. They have different cardinalities. Are they equal? Well, this one has XYZ and this one has WXYZ. They must have the exactly the same elements, so therefore that these are not equal. Okay? And then lastly, here we have A is equal to 1, 2, 3, 4. B is equal to a set containing 1, 2, 3, 4. They are equivalent because they both have cardinality of 4, and they are equal because they both contain the same elements. So The challenge below, determine if the situation below is possible. If it is, provide an example. If not, explain why not. Can two sets be equivalent but not equal? Well, looky here. We have two sets that were equivalent, but they were not equal. Okay, so we already have an example of that. Okay, can we have two sets be equal but not equivalent? Take a little bit, think on that. If you have a question or if you think you know the answer, or if you want to verify your answer, send me an email or write in the discussion board on Blackboard and let me know what you're thinking about that. This concludes part 3 of our basics of sets. Hopefully you can get into Blackboard and go into my math lab and start working on your homework. Best of luck. Thank you.